Hey, what's up, Cactus Con? It's good to be back. My name is Dan. I'm at Bishop Fox in R&D. These days, I've been helping build out our AI pen testing service, but that's not what this talk is about. If you want to talk about that, you can hit me up afterward, I guess. Yeah, I've been at Bishop Fox for over 12 years. I like to call myself, I like to say that if Bishop Fox were a D&D group, that I would be the bard, the jack of all trades and master of none. So I've done just about every kind of pen test there is to do at Bishop Fox, from web applications, ASP.NET and PHP, Ruby on Rails, to applications that were almost entirely written in database stored procedures, to physical pen tests and wireless cryptographic protocols, critical infrastructure, just absolutely everything that we do. And so I've got a lot of experience doing pen testing, and these days I help build out tools for the rest of the team. But enough about me. Let's talk a little bit about evading EDR using Wasm. So we're going to start with a demo. So first I want to just set the stage here a little bit. So on the right, what you're looking at here is a Windows VM. This is going to represent our victim machine. This is going to be the thing where we're going to run our stager. If none of this makes sense to you at first, that's fine. We're going to go through it all step by step. So we hit the wrong button. We're going to run our stager on our Windows VM. And then upon running that, we get a callback to what is on the left side here. There's a Sliver server. We can hit use to use that session. We're going to be using Sliver throughout the course of the presentation. As our C2 infrastructure, we made it here basically at Bishop Fox. It's an awesome C2 infrastructure. I don't have the time to extol its virtues for you here, but this is what we're going to use as a C2 infrastructure. And then we can run things like, who am I? It says Dan because this is my VM. We can get a directory listing. And it's basically a full shell. So this is a WebAssembly running inside for the payload. And notably, the thing that you didn't notice was Defender coming up and complaining and blocking. And that's mostly what we're going to be talking about today. Oh, this is, I think, just large enough of a group where I think I'll wait till the end to do questions. So if you have any questions, we'll definitely have some time for it at the end, but just sort of FYI. All right, so there I was on a red team. For the sake of argument, let's just call them bank.com. This is going to be our running example. We're doing a red team for bank.com, and there's lots of different services that we can perform as part of a pen test for bank.com, right? There's external network pen test, which is what it sounds like. You come in from the outside, attacking the externally facing infrastructure. Maybe that's websites, it could be anything. Physical pen tests of actually physically walking in the doors, obviously part of something that will do part of that. But for this moment, let's just talk about social engineering. Social engineering is a lot of where these sorts of scenarios are going to come up. So social engineering, of course, takes many places, many forms itself. There's phone calling, so we'll get on the phone and call up certain employees and convince them to do things that they probably shouldn't. SMS, or most likely these days, in-band messaging like Teams or something like that, messaging somebody in some form, trying to convince them to download something or give up some information or whatever. But of course, the tried and true method for social engineering is email. So we could focus on email for just a moment. So of course, email social engineering takes the form of getting a bunch of emails, and then by some mechanism, there's a bunch of ways to get emails these days. There's lots of marketing sites that do this sort of for free for you. There's people that validate emails entirely for sales purposes, because they want to be able to send sales emails to everybody inside of Microsoft. And so they have this big validated list of everybody that they know have emails. It's great for social engineering too. You can pay money to buy those things. You could also just do things like find the email pattern for the company. It's like first name dot last name at bank.com. And now you could just try john.smith, and he probably works there. So then naturally, you go ahead and send off a bunch of emails. But what actually goes inside of said email? There's lots of scenarios, of course, that you can go through, part of a red team engagement. It turns out that people will click on damn near anything if you tell them that there's a Starbucks gift card on the other side of it. You just say, hey, it was a really rough Q4. We just want to thank you guys. Thank you so much. here's a rewards portal. You can go to click on, get some Starbucks rewards. People will click on that shit, and it'll bring in some website that we make up to look like bank.com, or maybe even just something else, just employee-rewards-portal.com, and tell them that they need to download the Starbucks rewards app, because everything's an app these days. That's not weird. And then they'll be disappointed they don't actually get money. We should give them actual Starbucks money at the end of it too. They wouldn't see it coming. Just as a thanks for downloading our payloads. All right, so this is a high-level network overview of kind of what we're looking at here, right? There's the attacker running a Sliver client. So this is literally your laptop, like as an attacker. You're going to connect out to a remote cloud server. This is the Sliver server. There's actually multiple clients that can connect to the server. You can multiplay. That way, if you have many people on an engagement, you can all connect out to the same server and be connected doing these things. You can coordinate red team pretty effectively that way. Again, I don't have time to go over why you should use Sliver, but we recommend it. And then there's the victim machine out here. The victim machine will have downloaded some executable file through some mechanism. In our case, it could have been an email that they got, and they downloaded something. It could have been any other mechanism. Maybe this was even some technical hack, right? It's not terribly important for the purpose of this, but social engineering is the most obvious way to describe this. So let's focus on this just a little bit. So this guy here is the stager. We're going to talk a little bit more later about why it's called that, and why we go into this here. But if you set the stage again here for like the series of events that happen. So there I am on this red team. We send out a bunch of emails. We have a validated list of emails that we have for bank.com. That way the customer knows like who it is that we're emailing. We go through a lot of effort to put together a website that looks really legitimate for bank.com. We know we get hits. We can verify that people have downloaded our stager, they downloaded the exe, right? And we're just sitting and waiting for callbacks, waiting for getting a connection back from our payloads. And we wait, and we wait, and we don't get anything because our payload has been destroyed by antivirus. It gets caught. And this sucks. It sucks a lot for, I think, reasons that are pretty obvious. Now, it's actually not the end of the world a lot of times. Maybe even most of the time that we are doing these sorts of red team engagements, in fact, we're trying to test the security controls of the organization. That's part of the reason they hired us. So we might actually be adopting the like tools, techniques, and procedures of like known like malware groups. So like if the bank.com is really concerned with crypto lockers, they might want us to use payloads that would resemble crypto lockers. And so getting caught by the antivirus is actually just like a good thing. That's a pat on the back for the client. It's not necessarily a failure on our part. In fact, even if we did have some sort of like magical way to bypass the antivirus, they wouldn't want us to use that because that wouldn't get them anything. That wouldn't tell them anything about it. That said, sometimes we do, in fact, want to just get in, and it doesn't matter how. And bypassing antivirus is part of our job. And so this is where we were. Getting caught by the antivirus, egg on our face, and I do not like egg on my face. So anyway, a little bit after this, I was having a talk with my buddy Joe. And so I was telling him about this exact scenario, about how like, oh man, we just kept on getting caught by the antivirus, and it just sucked. And I felt like we didn't have a good look there. And so I was telling him about some cockamamie scheme of mine. I'm saying like, all right, why don't we like make our own custom language with like a custom interpreter? And then we could take the language, we could put it through the interpreter, and we get like a binary, right? That like nobody would ever be able to like understand. Like the antivirus would have no idea what's going on here. Maybe to like zoom out a little bit, understand like what I was getting at here. So we, for the longest time, had gotten away with just using Golang binaries because slivers were in Go. And Golang, you have to understand, while it's a compiled language in air quotes, it actually has a lot of infrastructure behind it. It has a whole Golang runtime that is like embedded into all Go binaries. It doesn't compile in quite the same way that like C or even Rust does, where like, you're really making machine code. Like there's this whole memory management infrastructure. There's a whole bunch of stuff behind that. And so this doubles as a kind of obfuscation layer. So for the longest time, we were able to make Golang malware, and the EDRs just had no idea what was going on. So the antivirus would try to understand what's going on inside of the binaries, right? And of course, they can see the executable, they can see the code, but they're not able to really introspect it. It's all kind of pre-obfuscated. And so for the longest time, we just had Go binaries, and things just kind of skated right through. And then I guess two things happened. One is Sliver started getting more popular, and so the antivirus companies started really picking up on Sliver specifically, and also some nation-state APT groups started using Sliver, and so the antivirus companies really started picking up on it. And then they eventually came to support Golang. So I think most, or I don't know, I couldn't possibly tell you how many, but generally speaking, antivirus companies are able to introspect Golang binaries these days. So you don't get a free pass for just having things written in Go. But this is sort of what's going through my head, right? How could we like relive the glory days of being able to just write things in Go and have it be kind of pre-obfuscated for us and just get past the antivirus? So anyway, this is why I was pitching to Joe, like, why don't we just do this again? Like, I just make my own Go, right? Like, I'd make my own custom language. And so anyway, he like looks straight at me and just says, dude, why don't you just use Wasm? And like, this sentence kind of broke me because like it didn't make any damn sense. So like Joe was the former head of our red team over at Bishop Fox, somebody who I respect deeply. And when somebody who I respect deeply and know is very, very smart says something incredibly stupid, it must be me that's just not understanding something, right? And so like I knew Wasm is WebAssembly. And it didn't make any sense because like you might as well have said like, have you tried using hyperlinks? But, like I know what those things are individually, but like how does that possibly help me solve my problem? So we began to explain. So obviously a WebAssembly, if you're not familiar, there is, imagine taking a step back here, imagine just going to bank.com in a regular ass browser. So you load up bank.com in Firefox or Chrome or whatever, and it serves you HTML and JavaScript. Now, the thing about JavaScript is that it sucks. And it sucks for a lot of obvious reasons. It's bad, and we've been trying to replace it basically ever since it's been invented. Very unsuccessfully. And so WebAssembly has been one of our more successful attempts at not destroying JavaScript, but at least supplanting it in part. So the idea behind WebAssembly is that the name is rather apt. It's like an assembly language for the web. So you can take this JavaScript, you can kind of cut out a little piece of it, and this is where the WebAssembly or Wasm goes. So you can define some function in WebAssembly, something that generally speaking, this is for the purpose of it, is maybe say like computationally expensive, like graphics, like rendering, or maybe you want to be doing like matrix multiplications or something like that, right? Something that JavaScript is just too slow and bloated to do in a reasonable sort of sense. So you say, I don't know, calculate stats or whatever. And then you can call this function from the JavaScript. So the page just operates like normal. You can write it in JavaScript, and you can take some chunks that are like computationally expensive and write those in WebAssembly. And what's really neat is that you don't actually write things in WebAssembly. It's a compiled target. So you write things in Rust or C or C++ or even Go, and then you can compile that to WebAssembly. That's kind of neat. So you can just have like literally like C code running in the web. And it's all nice and like sandboxed and stuff. And don't worry about the security for the moment. And so, yeah, you could see why, like, thinking about this, like, all right, I still don't get, like, how does this help me? Like, we have some web technology that, like, helps speed up JavaScript, and I'm supposed to, like, use that to bypass an antivirus? So, yeah, when Joe tells me, why don't you just use Wasm, this is still just not helping. So, he's beginning to explain. He's like, no, okay. So, you know how with regular websites, we found a way to take the browser, right, and strip the browser away and replace it with Node.js. So Node.js is basically like, instead of running the browser, you're now running it in this little container instead, and it can run as an exe on your local machine. So now you can run JavaScript, this thing that used to just be inside the browser, like on your local machine. And so you can access the file system, you can access the network. It's like sort of kind of sandbox, but not really. And people are very familiar with Node nowadays. It's like a completely ordinary thing. And so what I didn't know is that the same thing is true for WebAssembly. So there's these other programs, other frameworks, the most popular of which is Wasm that does the same treatment that Node.js does for JavaScript, but for WebAssembly. So now you can run your WebAssembly basically as a binary running on your local machine that compiles to a regular exe. So the outer core of this is Rust. At least the binaries that I've made here are Rust. This could, in theory, be any compiled language, but we're going to be talking about Rust. It just so happens that Rust and WebAssembly kind of go together. The people who do a lot of Wasm development just really like Rust, and people that like Rust, they just, I don't know. They don't have to be the only pairing, but they just tend to go together like peanut butter and jelly. So this, again, can access the file system. It can access the network. So you can do all the things you would need to do, like from a payload perspective inside of this WebAssembly. And what's critical about this is that this kind of serves as our obfuscation layer. So when you are running things inside of WebAssembly, you can stream like instructions of WebAssembly to the system, right? And it's being interpreted by this live interpreter. And also WebAssembly is this like really bleeding edge technology that nobody is really paying much attention to these days. I literally didn't even know this was a thing at the time that Joe was talking about it. So the EDR companies have like no support for this sort of thing. So we're going to get this exact same effect of the antivirus companies can absolutely read everything that's going on in the outer shell of this, inside of this outer binary. But on this inner shell, inside of the WebAssembly itself, it's all just kind of pre-obfuscated. It can technically see the code that's running, but it just can't really make head or tail of it. So let's return and talk a little bit more about the actual payloads themselves, about exe. So returning to our network diagram, we again have our attacker connects out to a Sliver server that we're going to be listening to callbacks for. And then we have our stager. It's installed into the victim machine. So the stager is actually really simple. The stager is really meant to be just like the initial entry point of the system. That's the thing you actually email out. That's the very like tip of the spear in terms of exploitation. So it's very small, very small bit of code, as we'll get into a little bit later here. And it can only do one thing. It doesn't have a lot of malicious code in it. All it wants to do is download like more code. So basically this. Imagine being given a magical lamp, right? That can make exactly one wish. There is only one correct wish in this scenario. You should, of course, wish for more wishes. And that's the point of stager. We can run one command, and the whole point of the stager is to run more commands. So the stager doesn't do much of anything. It's just the first stage in a staged payload system. So there is this thing here. This is the exe. This is the stager. And then up on the server, there is the implant. The implant is where like the actual malicious bits happen. This is the lion's share of the code, as we'll get into later. And it's also really like where all the interesting things happen. So the stager, in fact, the stager I'll be releasing just shortly here is about like 230 lines of code. It's really small. It has three main jobs. The first is to make a request out to the C2 server, just to register itself and like initiate a download. Step 2 is to download the implant. And step 3 is to run the implant. There's really not much it needs to do in this process. So that's why it's so small. And the reason it's also so small is for like a couple of things. One is small binary size. So you want to be able to, again, email this to people or send it over an instant message, or like, you don't want to be sending people like 200 meg downloads, like, here, please download this. And it's like 200 megs, and they're like, maybe they're in a coffee shop, but the Wi-Fi sucks. And you definitely don't want your payloads to be failing because the coffee shop Wi-Fi sucks, right? So the whole point of the stager is that it's small. You can send it to people, and they can not really think much of it. Also, there's a little bit of EDR evasion value to it being this small and so simple. If you think about this exact process of like requesting the C2 server and then downloading some code and then running it, this is basically just describing an installer. Like if you go to Steam and you download like Steam, like the first thing you download isn't like a gigabyte large. Like it's a small file that then downloads more files and then runs them. So this pattern isn't necessarily like, inherently very malicious looking. So that's also a good reason to do this. So we're going to go over some of the code. I'm not going to bother you with like all of it. That would be insane. But here's some of it. This is, of course, in Rust. So the first thing is to just request the C2 server. Maybe some of the defenders in here are thinking, "Ooh, look at those strings that I could signature." Don't get excited. So any Rust functions that end with a bang and exclamation mark are compile time macros. So like include string is just a compile time macro to include the implant URL like at compile time. So that string doesn't appear there. And same thing with the debug prints. Those are just debug macros that only appear in the debug builds, not in release builds that'll actually appear in real things. So none of those strings will actually even appear, ever get compiled into the final compiled binaries. All this is doing is just using the Rust built-in HTTP library, urec. I just decided to use HTTP to download the initial payload. You could do this using anything. You could do it using DNS. You could do this over just a raw socket. HTTP is fine. I just wanted to get something to work. And the HTTP libraries are pretty simple to use. But this is pretty easily swappable out for just about anything else. Same thing with downloading the implant. This is just using a basic, like how to download things over a HTTP socket using Rust. Just define a buffer, put the payload into the buffer, into memory, so the whole thing in memory doesn't hit the file system. And again, these strings don't appear inside of the binary. You run the implant. So like I said before, we're able to hit the network and file system and such, but not by default. So Wasm time and basically all of these runtimes will by default lock down like the ability to hit external things. So one of the like selling points of Wasm time, like why would you ever want to run Wasm on your local file system, is specifically to kind of run a pseudo sandbox around maybe untrusted code. So you can have, like, rather than using something like Docker, you can have nice, efficient, like, WebAssembly code, and then run it, and then it could run inside of this pseudo container, right? It's not able to write to the file system. It's not able to access the network. It can't make DNS requests, anything like that. So we just turn all that shit off. So that way we can access the local file system. We can do all the things. We can copy the environment. We can do whatever we want. And then you just invoke the implant. It of course is interpreted, so we have you have to WebAssembly runs these days in a component model. It's not important here, but you have to basically define your functions as a component that are imported. You instantiate it, you link against it, and then you run it. We just find the run function and then run that function, and then that's the malicious code. Cool. So now we have our victim running the implant code, and that is how it works. So we're going to talk more now about the implant, because the implant is where all the like interesting bits happen, and frankly, where most of like the lion's share of effort in me building this tool actually happened. Like I said, the stager is pretty simple. It's like 230 lines of code. It's just a minimal set of things just to do those 3 steps. The implant is where all the goods happen. So at first, I wrote a really basic proof of concept implant that didn't really do much. It just kind of like made a direct socket call out to some server that I could like, you know, echo things back and forth through and say, hey, cool, isn't that neat? And it's neat, you know, it could have run shell commands maybe, I guess, but 2 things, like one, that's not really a proper C2 channel. And also, this was unencrypted because, of course it was, but I just made a simple socket connection. And if there's one thing my buddy Joe does not like, it's unencrypted shells on engagements. So I could not let that stand. So building out this implant. Now, the first thing you might think is, why don't we just use Sliver? Sliver as an implant. In fact, it's written in Go. And didn't you just moments ago tell me that Go can compile to WebAssembly? And this is true, except that it only compiles to the kind of WebAssembly that runs in the browser, and unfortunately not the kind of WebAssembly that runs on an executable. The kind that runs an executable is called WASI. WASI is the WebAssembly Systems Interface. Specifically, we need WASI P2. P2 is the preview 2. It's where networking was introduced. So if you don't run specifically P2, or I don't think P3 is out yet, you can't make network requests, which isn't any good for us. It's not useful. Yeah, that sucks. That would have been really handy if we could have just used the Sliver binaries. Though in truth, the Sliver implant does a lot of like shenanigans with the Golang compiler, and it might not have worked anyway. So I guess fuck it, we're gonna make this on our own. So implementing a WebAssembly implant for Sliver. Step 1 is mutual TLS end-to-end back to the C2 server. I'm going to highlight just a couple of major features that I implemented here. I couldn't possibly go through all of them. The one thing I wanted you to get across is just how hard this was. It fought me every step of the way, and I just want to let you know that this was difficult. So mutual TLS end-to-end back to the C2. So of course, we're running inside of this victim machine here. The executable is inside of this victim machine. It's split up into two pieces, as we described. There's the stager, this outer shell, and the WebAssembly, this inner shell. So of course, the simplest and most obvious thing to try is to just use the host TLS. So you can just use the outer stager's TLS library, right? Now this works and it's encrypted in air quotes, except of course the antivirus can read it. Even though it's encrypted, the antiviruses hook into the local system's TLS libraries and certificates, and they're able to read all the traffic. So you just kind of can't do this. This would prevent like outside entities from reading our traffic, but that's not the point. We need to prevent specifically the EDR from reading our traffic. So this is just a no-go. This would have been really easy, but obviously that doesn't work. We have to run the encryption from the WebAssembly itself. So where does that leave us? The first thing I tried, of course, was the WASI TLS. This is a project that says it wants to do exactly what I want to do, which is a WASI SSL/TLS interface. However, if you read the fine print on it, it says that the encryption work is done by the host, which isn't what we wanted. So this is done for like probably good engineering reasons. There's subtle and unavoidable timing attacks you could do against cryptography when it's inside of this kind of managed environment, for the same reason that doing like crypto in JavaScript is kind of like frowned upon. You don't have constant time operations that are reliable, and that's just not a thing inside of WebAssembly yet. So like there's subtle ways of breaking encryption that would be done inside of WebAssembly. For my purposes, I don't give a shit about subtle timing attacks, right? Like that's not a thing that the EDR is going to do again. Like our threat model is the antivirus, and like if they're aware that we're using WebAssembly, like they could just do something else. But in a normal circumstance, yeah, I totally get it. That is a reasonable engineering choice to make. So the next thing, of course, is just Tokyo Rust TLS. This is just the standard TLS library for Rust. Like if you just write a Rust program, this is the standard TLS library they use for that. Naturally, because I'm talking about it, it obviously doesn't work. There's an outgoing issue on GitHub from 2021 saying, hey, wouldn't it be cool if we could make this work in WebAssembly? And the latest comment is from 2 years ago. So that is not yet supported. And I don't know at this point that it's going to happen, because it, again, probably depends on things underneath them, like compile or constant time operations inside the WebAssembly runtime itself. So that was a bust. And that brings me to OpenSSL. We're already doing things in hard mode, so fuck it, let's just do it in hard mode again. Luckily, there is a project that's OpenSSL-Wasm that says it has precompiled binaries for OpenSSL for WebAssembly. It even says up-to-date and maintained, though there hasn't been an update in 10 months. So I guess maintained and up-to-date is a relative sort of term. The bad news is that their precompiled binaries are precompiled using Wasm32-WASI, which might really look like it's what we want, and it's so close. But we need WASI P2, or else it can't do networking, which we really need it to do. So I guess I'm going to have to compile OpenSSL myself cross-compile this to WebAssembly. And look, compiling OpenSSL in the first place is a pain in the ass, let alone cross-compiling it to some new cockamamie thing. So, all right, we're going to try that. First, I wound up having to stub out like get PID and some other functions. So like when you're in the WebAssembly like environment, you don't have a process ID, so you can't call get PID. So I wound up just having to like take all those and stub those out. You have to take out some of the rand functions too, because it's like trying to access like some rand system calls or like operating system things that just don't exist inside of this WebAssembly infrastructure. So whatever, it's fine. I got that to work. Finally compile, and we have some .a files at the end of this, some library files that are WebAssembly compiled binaries. I was happy with myself. We also have the corresponding SSL.h files, because of course it's a C program, so I have C header files, which you cannot use in Rust. So we have to then use a separate program. Rust does have Rust bindgen, so you can use this program to take your C header files and convert C header files into their corresponding Rust sort of programs. Naturally, this immediately failed to work. All the types were wrong, or at least a lot of the types were wrong. It like got like longs and like, it was almost all just integers for some reason. I don't know why. But fine, eventually worked through those errors, and eventually we have an OpenSSL.rs in the repo that works in Rust. It's 43,000 lines of code, but don't worry about that. You don't actually have to read those lines of code. It's just a header file, basically. We don't even really need to use a lot of this stuff. We're just going to use a very small subset of the OpenSSL code. But we can, in fact, call OpenSSL now from our WebAssembly. And so you might think it's time to have the ribbon broken. We've got OpenSSL running in WebAssembly, but of course we don't. It would never be that easy. Here's an example of a typical OpenSSL program. This is just from the wiki on OpenSSL. OpenSSL is notoriously difficult to use, like by hand. This is, of course, in C, but it's fine. All of these same functions exist inside of Rust, but just a slightly different interface. And the problem here is at the very bottom. So we have our connection. This is the like standard way. This is the easy mode. So we're already within like a hard mode within the hard mode. But within this track, we're still maybe having a glint of an easy mode of being able to use the like standard, like high level OpenSSL functions. The problem here is that we make the OpenSSL wants to make the network call. We give it the host name and the port, and it makes the network request, which doesn't work in WebAssembly. We have to give it the socket. So this doesn't work. Instead, we have to use the bio interface, the basic input-output interface for OpenSSL, which is miserable to use. Everything is manual. This is the hard mode within the hard mode within the hard mode. It's just miserable. You have to split the input into separate things, so the socket is actually input and output. This is all a bunch of garbage. I'm not going to try reading this to you. All the socket code is non-blocking, of course, because it's not threaded. We've only got one thread. So anytime you want to read or write to anything, you have to loop over it and just keep on saying, "Are we done yet? Are we done yet?" It's just kind of awful. This is like 1,000 lines of code just to like read and write OpenSSL. It's insane. But at the end of that, there was light, and we were finally able to run OpenSSL within WebAssembly. Except of course not, because it immediately crashes. So have you ever had one of those bugs where like you're pretty sure that like you're doing things so normal that like you might be the first person ever to run this code? Because like there's no way that like this is a proof of concept for crashing WebAssembly sockets, right? If you literally, this is it. You just make a connection to a server. You get three objects: input, output stream, and a socket object. For whatever reason, there's three of them instead of just one. Whatever. Don't think about it. You read from the thing, you write from the thing, and then you like close out the context. And this crashes it. So after a bunch of back and forth with some of the developers, it happens that those three objects have side effects when they're cleaned up, and you have to destroy them in the correct order. And Rust objects are automatically cleaned up by default in the order in which they are declared, which is a bit unclear here, but this is not the correct order. So basically the solution to this was just to manually drop these to be super duper sure, drop them in this exact order, and then it stops crashing. And then we actually are able to make OpenSSL calls and have encryption from within inside of WebAssembly. Yay. All right, so there's a couple of other major features inside of this, which were equally as painful, but not in nearly as interesting a ways. So there's a Sliver-compatibility. So just because we can make a TLS call out to our remote server doesn't mean we can actually talk Sliver speak. Luckily, Sliver was written by Joe, and Joe is awesome. And it uses protobuf as the main mechanism for talking back and forth. Protobuf has great Rust support. So it was really just a matter of importing the protobuf definitions, and that was awesome. This was actually a pretty good, it was mildly painful, but just in a normal programming sort of way, not in a made me want to quit my job sort of way. So that was pretty good. And then lastly is SOX 5 proxy support. So when you're doing these sorts of engagements, when you're running a malicious code on this victim machine here, imagine we email this out to somebody, right? A lot of the people that we're emailing aren't actually that interesting of targets. In many cases, the thing that you're interested in is this internal network. You're not actually per se interested in the computer itself, but using that computer as a springboard into some other server that really contains the juicy stuff. And so we want to be able to proxy our traffic through that victim machine into the rest of the internal network. And so having an open SOX proxy is exactly the best for it. I wound up just writing my own SOX proxy from scratch in Rust. It's there in the source code. You're going to see it. There, of course, were existing SOX proxies in Rust, but they all made their own socket connections, and you just can't do that inside of WebAssembly. So I had to write my own that could piggyback on an existing socket connection rather than one that required you to use theirs. That said, SOX is like a 25-year-old RFC or something like that. It wasn't that bad. It's a very straightforward thing. You just there's one handshake back and forth, and then you just shove data in, and then it pipes it through. So it wasn't that bad. But I did have to write an entire SOX proxy from scratch, so that's fun. Got to do that. And so those are the three, I don't know, major features of our implant here. So after that, we wanted to give this a test run on some EDRs. So I can validate, at least as of the time of me speaking to you now, that this successfully runs and can do all the things against Defender, Palo Alto Cortex, and Sentinel-1. Those are at least the machines that we, or lab machines we had set up internally that we were interested in running some payloads against. So at least against these ones, we could have the payloads really running and doing SOX proxying and Sliver operations, all that stuff. I did run the stager itself through a virus total, and it got a pretty good results. I'm going to be honest with you, I had not heard of Icarus or BCAV Pro until I ran this through virus total, so I don't know, maybe good on them. CrowdStrike Falcon had a low confidence hit, but whatever, it's red, I'll give it to them, good job. And Google, didn't see that one coming. I guess it's their browser detection thing. It's not like an antivirus you can install on a desktop. It's their built-in antivirus thing that's in Chrome, I guess. But for the most part, this gets through. Mind you, the stager is really straightforward. I had no evasion techniques baked into the stager whatsoever. It's literally just a Rust binary that runs those functions that I showed you earlier. So we didn't do any compile time obfuscation or anything like that. It's not packed. All right, so there is the release. If you go to github.com/bishopfox, you'll find under the Sliver Wasm stager. This is open source right now, so you can hit it. I know one thing that you're probably wondering, a good question, is hey Dan, so if you're releasing this online, open source, won't the antivirus companies just sort of catch on and start detecting this? So I have a couple of responses to that. One is, the Go binaries lasted pretty long, so this might too. But I'm releasing this archived only, so it's pre-archived. You get there, you'll see the big banner on the top of GitHub that says this repo is read-only. I'm not going to be accepting pull requests. I'm not going to be accepting issues. The point is that this is a one-time release as is. The reason is that I'm going to be keeping my own sort of like evasion stuff private, and you should just probably do the same. The basic technique is here, and you're free to modify this. If Defender starts catching it, just perturb it slightly and it'll be fine. Also, in a world of AI coding agents, it is exceedingly easy to then take this, feed in the prompt, hey, change literally everything in this program. Change every line of code, but keep it logically the same. And it'll just do it. Like it's really easy to make these sorts of modifications to source code now in a way that you just couldn't previously. So the implementation is provided to you as is. Also, it'd be really straightforward to take this existing Wasm time interface, even if the antivirus companies went all out and were finally able to introspect the binaries, right, or able to understand the binaries that Wasm time is producing. We could just take that and swap it out for a different one. There are other competing Wasm runtimes that each would have their own sort of quirks and idiosyncrasies that the antivirus companies have to independently support. And that's not even, you know, the idea of me making my own custom language and own custom interpreter is still on the table. Don't make me do it, because I will do it. And so, yeah, this is the release. You can feel free to download and use those. Let me know how it goes, but I won't be taking pull requests. And then that's about it. Thanks very much. We can do some questions if you have it. Remember, a long rambling statement followed by a what do you think about that is technically a question, but not a good one. I took that from Cory Doctorow. I like it. We don't have any questions. We can end here. Question? Thank you very much. Cool, okay. Oh, no, we've got a question here. Yeah. Oh, yeah, sure. Let's see, do we go back in time? Honestly, it's not that like interesting of a demo. It's kind of just me running a payload and getting a sliver call back. So yeah, we get the stager.exe, which is literally there on the desktop. I could have double-clicked on it, but whatever, I ran it from terminal. We get a connection back to our implant here, to our Sliver server. And then from here, it's just Sliver functionality. You could say use to use that session, because we just got the session in, and then built-in commands for who am I and ls, which isn't actually running a shell command, who am I and ls. Those are Sliver commands. So Sliver already knows like how to run a directory and stuff like that. So one of the things that you don't do from inside of WebAssembly is direct shell commands, because you want to be able to do everything inside of the WebAssembly, not outside of it. And so a shell is naturally on the outside of the WebAssembly. So all the Sliver functionality is there. That is to say, things you'd want to do, accessing the file system, reading, writing, copying, all that stuff. But yeah. Good question. No. Well, so I'm being a bit glib, but like, one, that's a difficult game, and two, like, it really looks like an installer. I think there was a question here. Yeah. Oh, this is just Defender. Yeah. Like I said, we tested against Defender, Palo Alto Cortex, and Sentinel. Those are the things that we had like definitely manually checked here, there. Yeah, that was it. Okay. Against the full runtime, against the larger virus total list, I couldn't possibly actually get samples of those and independently run each one of them. So, yeah. Thank you. Cool. Any other questions? Yes. Yeah, so the basic question is like, I guess maybe summing up the question in case you couldn't hear was like, is there's two connections that come out, right? There's the initial like download of the payload, and then there's the actual malicious commands afterward. Like, does it not catch either? So the first thing is more dangerous because it's not encrypted. It kind of by like definition can't be because we haven't run the implant yet, so we don't like know that information. So it's not like end-to-end encrypted, I guess. You could, there's more fancy techniques. In my stager for this, I just made an HTTP call. So it was pretty straightforward. You could do fancier, more advanced things than that, absolutely. As far as the stager is concerned, there's many more advanced things you could do, but apparently just being a Rust binary and just doing the things is pretty good. Good enough to get past most of the EDRs. Oh, that's not it. Yeah. No can defense. No, what is the defense? That's a good question. I'm not a blue teamer, so I feel like my initial answer is that's not my problem. I mean, there's obviously some behavioral stuff. Like if you were to, I feel like there's some fishy stuff that I'm getting into here that like maybe some behavioral analysis could like identify. But yeah, I don't know. You're definitely gonna be playing whack-a-mole with having the different runtime libraries. Like there's so many ways that I could run WebAssembly inside of this binary that the moment you try to like introspect it, we could just pop that out. So yeah, that's tough. Yeah. What's the sorry thing again? Edge defenses. Yeah, so of course if you try to if you don't allow outbound like HTTP requests or something like that, that would have blocked my like egress mechanism. Something like that. Yeah. Like, so absolutely those things are things that we tried to research ahead of time when we were doing red teams, that we are like reasonably confident that the payloads we're making can actually get out. That's why I suggested maybe DNS. DNS is usually allowed out. It's a bit more painful to do DNS in that mechanism, but you can implement that. That's definitely possible. Yeah. Yeah, binary signing. Yeah, there's definitely some other like, if you're able to, you can like lock down like more like endpoint detection, or not endpoint detection, but endpoint like protection mechanisms, like allowing only binaries that are signed by some corporate like binary sign, right? Yes, though in practice, a lot of organizations just have a hard time with that sort of thing. Like one time, you know, the like CEO needs to download like something and run it, and the laptop stops him, and then like that's it. EDR is out the window now. Like you're not allowed to anymore. Yeah, yeah. Mm-hmm. Mm-hmm. Yeah, and of course, in some cases, you can piggyback on existing process or existing infrastructure. So maybe you can't run arbitrary EXEs, but maybe Python.exe is already there, and so you can just run the Python interpreter, and then you can just piggyback on that. So there's there's ways, but that might there's ways of locking that down. I don't know. I'm not a blue team guy, so. Any other questions? Good. Yes. Yeah, I think 100%. Yeah, a big reason that this works is because Wasm is really new, and that it is in a state right now where it's like barely functional. Like it works is like the big selling point for it. So that's a double-edged sword. It's kind of a pain to work with, but also like I legitimately didn't know that this was a thing before starting this project. So what are the chances of like EDRs being able to introspect that runtime? Like, just not happening. Yeah, and that. Oh, I alluded, what the question was, what is the point of WASI if not malware? I mean, wow, it does a pretty good job of malware, so I don't know. No, like I said, I think that a lot of people sell it as like this like containerization process for like, that way, like super Docker lights, you can put some like hyper efficient Wasm inside of this little thing and then it can run and it's kind of this lockdown environment. So it's not quite sandboxed, but it's like pseudo sandboxed. Oh, maybe. Either, I'm not the right person to ask that. Yeah. You back? Yeah. Yeah, so like what are persistence? Do we need to escape from the jail? I don't think there's any need really to escape from the jail that is the WebAssembly runtime, because we have full control over that from inside of the stager. So we just turn off all of those flags. So we can, write to any file. We can write to the, we can make network calls. That's like most of what we want to do. Anything else, you can, in theory, make a little shim that's on the outside that's in the stager, but I've avoided doing that because I didn't want to have any malicious functionality inside of the stager whatsoever. I just wanted to have it execute WebAssembly and then be on its way. Yeah. Yes. Oh, longer than I'd care to admit. I probably worked on this on and off for like a couple of months. This was actually quite a while ago too. Just about a year ago, I wrote this. So we've been like playing around with it inside, and then I honestly wasn't going to release it. And then both my boss and his boss independently said like, "Oh, that sounds really, really cool. You should like give a talk about that at a conference or something sometime." I was like, "Oh, all right, I guess." So now you get to play with it too. Any other questions? Yeah. Oh yeah. So this guy. So I work at Bishop Fox, of course. I'm R&D over there, but longtime pen tester, and I still do consulting engagements regularly. So yeah, I think that's about all for me then. Thanks a lot for coming out.